Hello, everybody. How are you? Uh, Saidi Magres Tube brought you a new topic about a new lesson about circular motion and oscillation. Okay, today we'll see how circular motion and oscillation can be related, and one helps to understand the other. Okay, so we know that circular motion is curvilinear motion along a curved path. Okay, circular motion is curvilinear motion. We can say it's also two-dimensional motion, but here we are going to treat circular motion associated to oscillation. Circular motion is a two-dimensional motion. The moving body follows a path made of set of points equidistant from a fixed point called center. Okay, so you can say this is a circle about which a particle moves around a fixed point called the center. Okay, this is going to be the path along which a particle moves. And you can choose always axes. This can be our x-axis, and this can be our y-axis. And initially, the particle can be, let me say, the particle can be here. The particle initially can be here, and let's say it is moving in this direction with some tangential velocity vt. So whenever you think of a circular motion, it's always true that you will have acceleration towards the center, okay, AC. Because the particle has mass, this acceleration is a result of a net force called centripetal force, so that you have mass times acceleration. Okay, you have Newton's. This is about Newton's second law, actually. So when the particle moves along the circular path, starting from where it is now, it is going to have, just assume, it's going to have a shadow. Now the particle and its shadow overlap, like when the sun is overhead, you will not have a shadow, just the shadow is below your feet. But when the sun shifts a little bit, you will have a shadow. Okay, so here, when the particle moves, let's say when it reaches here, its shadow is going to be here. When it is here, automatically it will have a shadow here. And when it is here, the shadow comes to be at the origin of the axis, or we can say at the center of the circle. And as the motion continues, the particle will have its own shadow on the x-axis, but when it reaches on x-axis, okay, completing half a circle, its shadow is going to be below just the shadow and the particle overlap. Like the shadow is going to be under our feet when we stand and the sun is overhead. Okay, it is a circular motion, so it continues. It's circulating. Okay, it's circulating with a tangential velocity vt. So when it is here, you can see the same shadow on corresponding positions. Okay, corresponding positions. And finally the particle comes to the initial position on the positive x-axis here, which in other words means it covers, it is one complete circle. So if it continues, it is going to repeat the same motion again and again. It was here, now it is here, complete circle. When it goes, it is starting the same motion again, So it is a complete circle, means to go from this to this one and come back is going to be one period. Basically, you can say that is going to be 2 pi r over Vt. This is going to be the period completed. But if you are looking at the shadow instead of looking at the particle, if you look at the shadow, what you are going to see is an oscillation, not circulation, not a circular motion. Rather, you are going to see an oscillation of some dark spot between these points. Okay, between these points, the points that the x-axis crosses the circle, and that's going to be oscillation. It goes to the center, to the other point where the x-axis crosses the circle and comes to the center and goes. Okay, that means one complete oscillation. Okay, and oscillation, basically, if it moves, basically you will see such oscillations. Basically are going to be, you can see this is here. Okay, it goes to the highest point along along the way, and it goes to the same point where it started, and it goes to the lowest point, and it comes back to the point where it started its motion. So as there is one complete particle motion along the circle, there is one complete oscillation of the shadow of the particle. Okay, so the shadow is going to experience one oscillation, and the oscillation is going to be one wave. So the distance moved by the wave is wavelength lambda. Okay, wavelength lambda. So you can associate any quantity here to an oscillation. The period basically is going to be what? The period is going to be lambda over v. Wave of the particle, basically. Velocity of the particle. And this is t. So if you consider this one as one complete circular motion, and you can take the wavelength is going to be equal to the length, the circumference of the circle. That's why we say 2 pi r over Vt is the period. So if you understand oscillation, you can understand circular motion. If you understand circular motion, you can understand oscillation. That's why circular motion and oscillation are related. And whenever we talk about circular motion, we can associate oscillation as well, considering the shadow of the particle that performs circular motion. Okay, that's basically what is important here. So in circular motion, we know that there is centripetal force, okay? And this centripetal force creates centripetal acceleration, and the centripetal acceleration for uniform circular motion, okay? For uniform circular motion, you can derive that AC is going to be tangential velocity square over the radius of the circular path, And we know that when the particle performs circular motion, it is going to have angular velocity omega. And omega basically is going to be angular distance, okay, theta over time. And we can relate theta can be, it is going to be basically arc lengths for one complete circulation. It is going to be 2 pi r over r. Okay, whenever you take arc lengths and divide by r, basically it is going to be theta. Then theta for one complete circulation is 2 pi. Okay, and now omega, or maybe omega is going to be theta over t. Basically means it is going to be theta is 2 pi, and 2 pi over times r is going to be, we know that times r is going to be arc length or translational distance. Therefore you can say theta basically is going to be s over r, the arc length over r. That is what you did here. Therefore you can write instead of theta, you can write s over r over t, and it is going to be 2 pi r over rt, and omega is 2 pi over t, okay, or it is going to be vt over r. So there is a relation between tangential quantities and rotational quantities. And that relation basically starts with the definition of theta in radian measure. In radian measure basically means when s is equal to r, the arc length is equal to r, theta is 1 radian. That is the definition, okay? But basically theta, the angle measured at the center, which is a central angle, is always measured with arc length in radian, basically, when you consider not the angle, but the arc subtending a central angle. The arc subtending is the central angle, okay? That's how it works. So what we can say again is that the centripetal acceleration can be, because you can associate this one, Vt can be omega r. It is going to be omega squared r squared over r. So AC can be omega squared r. And centripetal force can be m omega squared r. And we can continue with that one actually. But my purpose here is, whenever we associate circular motion to oscillation or vibration, it is because we look at the movement of the shadow of the particle instead of looking at the particle performing a circular motion. Okay, so take this one, and we'll continue with the next concept with the coming video, and enjoy this one. Don't forget to subscribe, like, and comment.